All right, so I realized I left my stylus at home, so we'll get to use chalk today. That does mean, of course, that the video is not going to be as useful as it might otherwise be, but oh well. We had left off on Wednesday talking about embeddings, and we looked at using embeddings for input, right, into networks. Embeddings can also be used for output. So let me show an example. Let's say we got the ImageNet, right, where we have X as an image and Y as a label. We feed that into ResNet34 out to a softmax predicting 1 of 1,000 labels. Very standard, right? Well, let's slightly modify the problem. Okay? We'll keep almost the same architecture. What we'll do is get rid of the softmax and instead come out with a, let's say, a fully connected layer. Of size 300. Okay, why 300? Because we're now going to change. Y is not going to be the label anymore. Y is going to be an embedding. Okay? Of the label. So what we can do is take our favorite embedding, let's say Word2Vec, perhaps. Or we can use the Facebook's embedding. We can use Glove, something else. But let's try Word2Vec. Okay. So Word2Vec on a label is going to give us out what? What's the shape of this going to be? Sorry? Yeah, it's going to be a 300 by 1 embedding vector where we've got all these features which we don't have any particular understanding of what they are, right? They were just created as part of the training. So we get this pre-trained embedding. And we do this. And so now you can see how our training is going to work here, right? In that we have an X, which is an image, and we have a Y, which is an embedding, right? Which is, well, just say it's a 300 length vector, and we're trying to train to take a particular image to that vector. Take another image to the vector, so all of the golden retrievers that it sees, it's going to try and feed to the golden retriever vector. Does that make sense? How would we use this in practice? So if we wanted to do classification and find a golden retriever versus a finch, assuming finch is one of the 1,000 categories, if we feed in an image, how could we figure out what it is? It's easy when we have the 1,000 categories, right? Because we just find the category and that's it. But here we've got a picture that we feed in. So we feed in our, this is our happy finch, okay? It's not a terribly good looking finch. We feed it through here. We feed it back out. We get this vector. And now what?
You can measure like the vector distance between that and all the other labels.
So we could measure the distance between this vector and all the other 1,000 vectors that we trained our network on. Does that make sense? One thing we have to be aware of is how we measure that distance. So an L1 or L2 norm is not going to be great. When you're in very high dimensional space, you have this, well, they call it the curse of dimensionality, right? So this problem that stuff is all right around the edges. And so to speak, it ends up, and it just doesn't work well. The better type of similarity used is cosine similarity, where you're basically measuring the angle of the vector. So things with two angles that are the same in 300-dimensional space are considered close together. So, seems like a reasonable idea. We take this output vector, we go back into the 1,000 vectors and say which one's closest. Okay, so we do like a nearest neighbors for that. And that will work. It's slightly slower than just directly getting the category, but it'll still work. Yeah.
Are we training the embedding, or are we just
We're using a pre-existing embedding, so we'll take the existing Word2Vec embedding. We just download it from somewhere, and we'll use that.
What's the point of doing that?
Here's the reason. So let's, I'm going to move over to here if I could. So we have X, which is a picture, right? And we have Y, which is an embedding vector for this X. If we want to train our network, we have to make Y hat and Y be the same sort of things.
Oh, so you have embeddings.
Yeah, we have existing embeddings. They're the ground. We have two things that form the ground truth: our label for the image, and then the embedding applied to that.
Oh, so you're basically taking 300 and taking distance to that.
We're taking this 300, and we're trying to match this, and then we're trying to have this match up. We'll use the same similarity in terms of cosine similarity. So we'll be looking at the angle to determine what's close here.
I thought that these embeddings are used for like words to vectors, but now we bring images and like.
So let's look at what this is. Okay, so let's look at our original data. All right, our original, we have this image, and we have Y, which is 36. Right? What's 36? It's an index into a bunch of categories. Right? I'm not going to go all the way around to the back so that your necks won't get strained. So this is, let's say, person. Okay? Guess what this is? In fact, you can tell what it is because I'm going to put double quotes around it. It's a word. If we now take our embedding of person, that's going to give us these 300 numbers. Does that make sense? Okay. So this is our ground truth. We're just taking the labels, taking the text of the category name, running that through our embedding, and coming up with a vector. And then using that for our training. So we're training a network that learns to predict these vectors. Given an image, predicts a vector. And we can see it's not much of a change to the network, right? We're just taking the very last layer, which has the 1,000 softmax, and putting in a 300 fully connected. Okay, do we want sigmoids there? And the answer is no. We don't want an activation function because these vectors are basically unbounded. They're not between 0 and 1. Now, we went through all this work, and we found that we could still do categorization by taking an image, feeding it in, getting out a vector, and then looking, okay, what's the closest vector among our 1,000 categories? But there are other things we can do. Okay? We can find nearest neighbors among our validation set, training set, whatever set we have. Right? Basically, take this image, feed it through, get its vector, and then find the other images that have the closest vectors, which you can see here are pretty darn close. Right? So this is a way of doing image search. Right? But we're doing image search in our embedding vector space. Now, let's say we have one kind of fish in our categories, our 1,000 ImageNet categories. Is this fish going to have the same embedding vector as, let's say, a goldfish necessarily? No, a goldfish may be here, and this, I don't know what that is here, and a true fish is like up here. So it's really close. They're all a lot closer to fish than they are to lion. But different fish may end up with somewhat different embedding vectors. Okay. And so by looking at the similarity, we can find ones that appear to be the closest. Does that make sense? The other key thing is we can search for images not from the 1,000 categories, from beyond the 1,000 categories, which seems crazy. But we can search, for instance, for boat, which is somewhere in the embedding space, like say here, and we never trained anything on boat, but we trained lots of other things, right? And so any image that comes in is going to be fed to some embedding vector. And it turns out something like a boat will get us reasonably pictures of boats. So how do we find boats? We've got a bunch of images, and we want to find the boat images. We find the embedding vector for boat. It's not one of the 1,000, but it is one of the, whatever, 35,000 in Word2Vec. That gives us an embedding vector, and then we go look and find all the images that are close to that, which were not part of our ImageNet training set, right? Because our training set is just 1,000. Here's what else we can do. Just like we did arithmetic on vectors before, where we said, for instance, king minus queen equals man minus woman, right? Those are the same vectors. We can search, for instance, the embedding vector of a boat and the embedding vector of an engine and find the average of those. Neither boat nor engine is, either of them are in the 1,000 ImageNet categories. And we get, there's something that looks boatish here, and I can't quite tell what's going on. These are really poor. I don't know why they ended up so poor. Is this a, well, this has an engine, right? Is it a boat? I think it's a seaplane. So officially, we can count it as a plane or a boat, right? So, and this is a very narrow boat, kind of from this particular angle, it looks like. So, yeah, I don't know what I'd call it. Remarkable almost, right? That this can work. So we gained a lot of power by using learning embeddings rather than learning our actual categories. Or here, sailboat, also doesn't know about either of those. But we see here, it's certainly water related. I can't quite tell what's going on there. This is a sailboat. This is a sailboat. This looks like it was not actually a sailboat. Questions? So right, just because embeddings are used for words doesn't mean we can't bring them in to other problems. All right. Now I'm going to talk about attention. So let's say we're doing some translation. And we're translating, my example here was, let me actually go ahead and make an RNN. So El gato negro tiene hambre. Right, so this is our x1, x2, x3, x4, x5 feeding into our recurrent neural networks. We're going to be doing translation, so we don't output anything along the way. And then we go into, and I'm going to use a different color, right, because this is our encoder. And then we're going to follow that with a decoder. So the encoder encodes Spanish into meaning. Into a vector here, right? Because we end up here with a vector coming out. And we're going to then take this and start feeding out English. The black cat, and so on. This is called the right half of this? Yeah, a decoder. And so basically what we're saying is we're turning a sentence into, right, this part going right across here, which is a vector of however big we've chosen to make this R and N. And that this has to have enough information to come out with an English sentence. That's challenging, actually. It's challenging for two reasons. Well, one reason. And that reason is it's just hard to summarize sort of everything into here. We can imagine that there's useful information along the way that we are kind of forgetting about. It'd be nice if we could feed in the hidden state from all of these into our decoder so that we get more information. So you can imagine just instead of taking this input to the decoder, we're going to take a stack of all these as input to the decoder, perhaps. And we can think of it if you're translating, if you have a very long sentence, right, and you were translating into a language, you probably would not read the sentence and then turn that page over, right, because you know that page now and you know exactly what the sentence is, and then write it out in your other language. You would probably read the sentence first to get an idea of what's going on, and then start going kind of word by word or phrase by phrase or something. You'd first work on, let's see, el gato negro, right? And let's come up with what that is, and then tiene, and then hombre, or something like that. And if you were doing a language that didn't have the same word order that you were coming from, that you were going to, you'd probably be looking at sort of different parts of the sentence as you're doing the translation. You know, in order to spit out the first word, I'm going to be looking where in here? Well, in this case, I'm going to be looking here. And so in this case, English and Spanish have fairly similar word order. So as we're trying to output this word, we're kind of looking at the beginning. And as we're outputting this word, actually, let's just look at that. Can we just go word for word? Will that work? Can we just say, first word here, we'll just look at the first word here? Why will that not work, Laura? Here's an example. Yeah. Right. Yeah, so in Spanish, it's gato negro, cat black, as opposed to black cat. So there's certainly a switch that's happening. In some languages like German, you can, have a whole thing and then throw some verbs on at the end, say what's going on. So you're kind of left wondering exactly what the sentence is until you finally, hear the result. In Latin, the word order doesn't matter at all, right? It's all cases. And so it's just emphasis as to where you put the words. So what we're talking about now is what's called attention, okay? Where we're going to attend to various parts of the input as we're doing our output. Let me show you a video. All right, see if I can make this bigger. All right, so we've got this translation where we're translating l'accord sur and so on. And so we can see here, this is somewhat faint, but this is showing which words, and we're going to see how this works a little bit later, but which words are being attended to as we're translating from French to Spanish, and we get to the here. I'm sorry, we're going from, there's no Spanish, first off. This is English, in case you wondered, and we're going from English to French. So as we're outputting the la here, what words are we looking at in the corresponding English? And we're looking at, and this seems somewhat reasonable, the is the one that is most looked at. Next most looked at would be agreement, which kind of makes sense because that's what the is referring to, the article for the agreement, right? And am I correct that the la might be different if this were, feminine or masculine? You should not be the third person to nod your head. You should be the first person. Okay, so we can't just look at the, right? So we look at the agreement as well. And I have no idea why we need to look at signed. Is there any particular reason the verb would matter for the article? No, okay. So it was wrong there in terms of looking. If we look next at accord, yeah, it's mostly looking at an agreement. That makes sense. Sur is looking mostly at on, but at a bunch of other things. I'm not sure why, but someone might be able to tell us. Law, okay, so this is a good example where law is looking at the, most importantly, but it's looking pretty strongly at area because that's the noun that the is going along with. And it's doing a pretty good job of skipping across these. Economic, mostly looking at economic, somewhat at European, I'm not sure why. There's this idea of there are parts of the sentence that matter more than other parts of the sentence as you're doing your translation word by word. Makes sense. And if we could train a neural network to have this idea of paying more attention to parts of the input than others, that could be useful. That's what we're going to be doing. Okay? We're going to be coming up with a mechanism by which we can feed in. You can think of it as a subset, but it's really just a weighted average of all of these. Okay? Weighted average of the activation, the hidden activation from the first, the second, the third, all the way to the last. How we're going to weight that? Who's in the best position to know that weighting? The network is in the best position, so we are going to let it learn how to do the weighting. Does the concept make sense, though? Questions so far? So we are going to just imagine ourselves, that we'll construct later, an attention function. So the attention function tells us, E of t prime, tells us, so t are our time steps over here on the decoder, and t prime are going to be our time steps over here. So E of t prime tells us how important is the t prime activation to the t word. So for instance, would we expect E of 3, 1 to be high or low? What's the 3 represent? The third word, the third pink word or the third white word?
Cat.
Yeah, so cat. And the 1 represents L. Do we think this is going to be high or low? What would be the highest? The third with the second. Gato, cat, same thing, right? So let me actually just put this one here. E of 3, 2, high. E of 3, 1, I'm going to say is lowish. Probably not as low as hombre or tiene, but pretty low. Does that make sense? All right. And so when we're computing y hat, here, how do we compute this? We've got an activation function, which is the last thing we do. What activation function would we be using? Right. So this is nothing to do with attention yet. We're just going back to, in this RNN, how are we calculating y hat? Say again? Softmax, yes. So we'll do a softmax. And what's the calculation that we're applying the softmax to? It's like the same thing we always do.
All of the words.
Say that again?
All of the words. You're applying the softmax to it.
So we look at this RNN. First we calculate the hidden value, right? And what do we do with that hidden value? We feed it over here. And then how does it affect y hat? Multiply something like w, y, h times h, where do we put it up here? Of t. We just call that j. This is j, and this is plus by. Does that make sense? Right, weighted average with a bias, do a softmax. Why softmax? How many potential words are we outputting here? Right. We're saying there are 10,000 or 30,000 or however many words, and the is the one that it should be. So we'll be using an embedding here. We're not necessarily going to be using an embedding on the output. If we wanted to use an embedding in the output, yeah, it's harder to go backwards, right? It's easy to, given a value, find the appropriate embedding, but the network may be learning different embeddings, just as we saw in that example, and so we'd have to do a nearest neighbors or something to find the value. So we're probably not going to use an embedding on the output. Does this one make sense? Right, so it's nothing special. We're just saying all we need to know is the hidden state, and that allows us to determine what word to output. And we're going to say, you know what? That's useful information. There's more information that would be useful as well. That would be to add in something else. So what we'll do is have another weight matrix multiplied by C, where C is going to be our weighted average of all these things. So our context is what this is. The C represents context. So we've got our state, plus we've got some context associated with it. And we need to look and see what is the relationship between the context and these E's. First off, we want E of Tj, the sum over all j's, to be 1. Okay, because we're going to be using this weighted sum, and we want the weights to be equal to 1. So the E of Tj, this is E of T1, E of T2, E of T3, E of T4, E of T5. Sum of all this is 1. We want to say how much attention for each of these, and the total attention has to be 1.
Then you have the C T, and you have J for J. Where is that supposed to be a T?
Excellent, thank you. So these should all be J's, right, at the J. And what we're saying now is that the context at a given time period, where these time periods is all, as far as the decoder is concerned, is just the weighted sum of E of Tj times the activation at that time. So when we're outputting cat, we're going to use the hidden state here, which is a function of the hidden state from the encoder, right? but also reflects that we've output some words already. And we're going to say we're going to use a weighted sum of each of these 5 activations.
So is that essentially the 2 components being the E part for certain weighted average of the entire encoding and the H of J up until, say, the previous words of the decoder?
So let me make clear what will happen. Let me come up with some numbers for E31, 32, 33, 34, and 35, just so we can, so instead of lowish and high. We'll call this, so let's make ourselves a little table. So 1, 2, 3, 4, 5, and 2 is our highest one. That's like a 0.6, and a 0.2, and a 0.1, 6, 7, 8, 9, and 2.05s. Okay. Where did this matrix come from? It got learned, right? But we're just guessing what would be a good matrix.
Should we learn for every time step of the decoder, or do we just have the same count?
I'm going to show you what happens. Okay. Now, we would take H1, the hidden values here, and multiply those times 0.1. So 0.1 times hidden value 1 plus, I'm going to just use one color here, 0.6 times hidden values 2 plus 0.2 plus 0.05 plus 0.05. And this is equal to C3. So we're getting a lot of information from here, and a little bit from here, and less from the others. Why don't we just pick the words we want? Just say, I want, these 2 words. These are 1s and everything else is 0, or these are 0.5s and everything else is 0. It is kind of like the one-hot encoding. When we've got a label, and we're just back in ImageNet, those 1,000, we have our Ys look like 1 and a bunch of zeros. But our Y-hats don't look like that, do they? Our Y-hats are more spread out, right, as probabilities. And part of the reason we do this spreading is, in this case, so that it's differentiable. We don't want to just pick one of these words, or even a couple of these words. We want a nice linear combination that we can then learn various values for here, and that we can backwards propagate. That's really key. All right, help me out. Give me some questions, because I see some wondering faces, and that's okay. But I can't address until I know what the problem is.
So are we defining context to be the linear combination of hidden states you saw during the pink part?
Can you? I didn't hear the first part of that because of the fan.
Are we defining context to be the linear combination of hidden states? The attention linear combination.
The context is exactly as you say. It's a weighted sum of the activations from the pink, the encoder. So from every word in the encoder. And yes, we're going to see exactly in a moment how it learns that. Because there are some problems. It can't just learn a weight matrix from 5 to 5. Because their sentences are unknown lengths, right? So we're going to actually have to learn a function as opposed to a matrix.
So do each one of them only have one hidden state? What if they have like
There are multiple hidden states here.
So
Well, there are 2 ways to look at it. Each one of these is a time step that can have a bunch of neurons in it. Right?
right, because it passed its best, right?
Because we decide how big we want this to be. plus this could be a deep network as well, right? So we could actually be feeding up and up and up, in which case we just take the whole slice.
What was the original thing that happened? Like, was it just like you didn't use any of the hidden states?
What happened was, the original was, we didn't take any of this context, and we just said, we take the output from Hombre, and then that represents the sentence, and then we're going to feed that into here.
How did you make that output? Just the actual output?
We just, nothing particularly. Yeah. Creating the y hat is, yeah, without the pink, creating the y hat. But we're feeding in this hidden state just from one to the next. There's nothing that's really distinguishing these, except in how we're using them. So our context tells us, and let's just look back at that diagram here and see if it makes a little more sense here. So if we're looking, for instance, here, this is just saying that our weights, this is most of the weight, this is the rest of the weight, everything else is zeros or close enough to it. And we're now taking this weighted sum of the activations here in the encoder. Okay. And we do see how this would be useful, right? Or could be useful. In that we're focusing on the words that matter. So, how do we calculate this? How do we learn it, actually, the E of TT prime? Well, E of TT prime is a value between 0 and 1. So therefore, let's use a sigmoid at the outest layer. And let's use some information that might be useful to figure out what the right value of this is. So we're designing this function that we're going to have the neural network learn. So we will have some weights involved here. What do we want to weight? What would be useful to look at? Given the question is, how important is the t prime element here to the tth element here? What would be useful and what do we have?
Information surrounding the word? Is that
We could have information surrounding it, but what about information right there? What information do we have at t, let's say? So t is one of these. It's this one. T is 3. H of t minus 1 or h of t. Either one. Let's use h of t, because we can assume we've already calculated it, because we only need c for y hat, and we need h to have been calculated there. So let's use some function of h of t. What should we throw in front of this? Some weight. We got an e on the left side, so let's throw an e here and an h, and I'm going to call that hd because it's the h for the decoder, which I should really do here too, right? Because these both start from 1 and move on, and this starts from 1 and move on. We better distinguish them. Okay, so what do we have? We have sigmoid of WEHD. I'm going to erase some of this and rewrite it. I'm going to erase down here. So E of T, E prime, equals sigmoid of WE H D H D T. D stands for the decoder, as opposed to the encoder. Because what other information? So that tells us almost everything we have at time t in our decoder is represented in our hidden state. we want to know how important is t prime to that. What information do we have? H of t prime. H, I'm going to say sub e of t prime. So we have H, E, right, because it's the pink hidden states, at t prime. And I box myself in a little here. We'll use another weight matrix to say how important that is. So this is W, E, H, E. Always good to reuse the same variable to mean more than one thing. Sorry about that. So this is what we're going to define E of t prime to be. We're going to have to scale these e's so they actually sum to 1. Okay, because they won't necessarily sum to 1, but that's easy enough to do. And then we can calculate c based on that. So we're not really learning, as I said, this big matrix from how important is the third word here to the fourth word here that works for any sentence. Instead, we're just saying we have a function we've learned that tells us how important a particular word is here based on its hidden state with respect to a given word here based on its hidden state. So we're just doing a weighted sum of its hidden states. Take a sigmoid that gives us any.
What about the other hidden states? Wouldn't they be useful as well? Like the one like H of t minus 1?
In order to tell us whether what the value of E is?
Yeah, because didn't you say that? Yeah.
Possibly. We could extend this if we wanted to try and get more information. But well, there are two things. One, there is some information here about here because we're passing in this hidden state. And if we use a bidirectional R and N, then there's information in here, about Gato as well. So you could extend it for that. So the change that we're making programmatically is not very, so we're not changing the data. We're not changing the loss function. We're just changing the architecture by adding this to our calculation of y hat and calculating this E. Normalizing so they sum to 1, calculating the weighting average. But if we think of it in terms of code, it's not much code that we are adding. But it makes a big difference. This attention idea can be used for other things as well. So you can actually use it, for instance, for images. If you look at image captioning, right, given an image, try to come up with a caption for it. It turns out that attention can be very useful to focus on areas of the image. Say, the lower left-hand part of this image is very important to me right now because there's a girl there and I'm about to output girl. Questions before we move on to another topic? Drew.
So now the function E that we have, E of t prime, the two weight matrices that we have correspond to the t timestamp for like each of them, right? 1 and 1. So now we have 2 for each timestamp.
No. Here's our key. This weight matrix does not have a t in it. And this matrix does not have a t prime in it. This is a single matrix that says, given a hidden value at a particular time step, what should this weighted value be? It's a very good question. And the same thing true here. So, in fact, how many new weight matrices are we learning? Why 3? What's the third one?
These two and
Right. This one, and that one we're learning. And this is training, to begin with. The network is going to be like blindly looking at words here and says, oh, I'm translating cat, hombre. Yeah, that's a good guess. Oh, that's not very useful. Well, maybe I better adjust these weights a little bit. Right? And then, of course, what to actually do with this information as well is important. Okay? Maybe the context is useless. Maybe it's not. Maybe we certainly couldn't use this and totally ignore H, because we need to have some idea of what we've output. That's kind of important. So, okay. All right. I decided that I was not actually that thrilled with, I was not that thrilled with doing the notes directly within OneNote. So I'm back to true slides. All right. So what I want to talk about is autoencoders and generative adversarial networks. We're likely not going to do GANs today, and that'll push to Wednesday. So autoencoders we mentioned briefly. The idea is we train a network to learn the identity function. Now, some networks, it's easier to do that than others, but that seems like a stupid idea. It's like if you need the identity, just take the thing you've got and don't worry about the network. But what we've got is a bottleneck layer often. That is, the left part of this is the encoder, the right part of this is the decoder, and the middle part is the narrowest portion of the network. I am sad to say that it was not until last week that I realized where the term bottleneck comes from. Right? That, I'm not going to be very good at this. That is more like a Erlenmeyer flask or something. But in any case, the bottleneck is the neck of the bottle, and that's where the narrowest part is. So it also, years and years before I realized why Target's symbol looked like this. So, all right. So this is our bottleneck right here. In the sense that conceptually here, right, our input looks like it's, let's say a vector 300 long, and we've got a bottleneck vector that's maybe 50 long. And then we come back out to 300 long here. We know these two have to match in terms of size because we're trying to learn the identity function. And we have a y hat, and we would compare y hat against x as our loss function, right? Because of the fact that y equals x, since this is identity function. So this can act as a form of compression. We map our input to some lower dimensional space. An example where we've seen this? Embeddings is a great example. We're taking a admittedly very sparse 40,000 length vector and compressing that to a 300 length vector, but a dense 300 length vector. So this is the idea of autoencoders. Any questions on this before we go on to applications? Some of which, non-intuitive maybe is the right word. They required some creativity. Okay, here's one thing you can do. Let's say you want to learn to remove noise from an input. You've got a grainy camera. You've got a, let's say, audio input that maybe has some noise on it. And so you can learn to create a network that removes noise by creating an autoencoder, okay, where first you take X and then you inject some noise of the type you expect. And then you run your neural network, you get out a y hat, and you take your loss from your output to the original input, right? Not the X with noise. Because you don't want it to learn to reproduce an X with noise. You want it to learn to reproduce an X without noise. Does that make sense?
So in this case, you can kind of think of it as like inject noise as an encoder, and then our remove noise on the encoder.
I wouldn't think of it that well. The way I would think of it, I wish I could write on this. So the way I think of it is, right, we've got a sort of, there's an encoder part of this and a decoder. And I really would view it as a pre-processing step to the encoder. I was thinking for the moment, let's consider it as part of the encoder. But the way we're going to use this later is that we are going to be encoding and decoding random images that have noise. And so therefore, it makes most sense to think of the encoder here as an encoder that takes images that might have noise. Okay. Does that make sense? All right. And depending on the amount of noise we're adding here, the size of the bottleneck layer, it can do a good or less good job of this. Deepfakes. How many people are familiar with deepfakes? How many people have heard of deepfakes? I see one hand. Raise your hand. Come on. All right. Only one. All right. That's interesting. So this is a suitable for work demonstration of deepfakes. So, but it's used as a way to, for instance, put celebrities' images onto nude photos or videos. And it's deep learning, and it's creating fakes. So fake news, fake videos, fake pictures. Just for research purposes, I did go to look for some of these. There's a subreddit on deepfakes, but it turns out that has been banned. So no longer here. And what happened was there was a user on Reddit named Deepfakes who came up with a GitHub repository with basically an end-to-end pipeline of creating deepfakes. So come up with 300 or 400 images of your celebrity, come up with 300 or 400 images that you want to put it into, train, do some stuff. And unfortunately, this led to a lot of script kiddies who create deepfakes. So. All right, so here's our example. So you take hundreds of images of the celebrity and then some model. The model is the one that you're going to want to use as the body, and you're going to put the celebrity's face on it. So here's what we're going to use. Our celebrity faces are going to be, give me his name. Nicolas Cage, thank you. All right. And give me his name. Yeah, so Donald Trump, I'm going to call him a model and not a celebrity. So, whoops. Excuse me for just a second. All right, I need to restart my recording. All right. Then what we do is we are going to use autoencoding to try and solve this. So we're going to have an encoder that works with a celebrity decoder. So the both encoder is an encoder that we're sharing among the celebrity and the model faces. Okay. And we'll see why that's important to share them in a moment. So we take the input. Because we have a small amount of data, we do a lot of data augmentation. So they actually warp it. I just showed a rotation here, but there's an actual skewing and warping that happens as part of the training. So the idea is this is our input, this is our y, and we're going to get a loss of whatever this y hat is coming in with. I am sorry, but this is an error here. This should be y, because x is warped. We're not trying to make it learn warped. We're trying to make it learn to unwarp. So we're looking at the loss of what's coming out of our network with our unwarped version. And And the problem is I'm calling the warped input x. If I wanted, what I could have done was we could have fed x in here, said there's a warping process, and then we would have been correct to compare y hat against x. But just make a note here, we're comparing against the unwarped version. Y is the unwarped version. X is the warped version. It was perhaps a bad terminology to use. Okay? But this is what's going in, and Y is what we actually want to be comparing against. So we can see how this could work, right? And our hope is that this, what we'll call a latent face, our embedding, because we're basically embedding our celebrity faces into a vector, will contain some nice high-level information. Okay? About, I'm not sure, eyes, where eyes should go, or this might say there are 2 eyes of this size and a mouth here, and what it doesn't have to do is represent what Nicolas Cage's eyes look like. Why? Where could the color of Nicolas Cage's eyes be represented in this network? In the decoder, right? Because this is celebrity decoders decoding the celebrity, and it's Nicolas. This is not all celebrities, right? This is the Nicolas Cage decoder with our images, and so it knows his eyes are whatever color they are, right? And whatever color his hair is, assuming we don't take pictures from Face Off. Wasn't that something he was in where he had a face transplant? That'd be a bad choice for this particular exercise. Okay, so there's nothing Nicolas Cage specific in here necessarily, because all the Nicolas Cage specific stuff can be here. Similarly, there's nothing Donald Trump specific here. We can have that all in here. So this can completely represent how his hair looks, which is probably a fairly large network, just on its own. The reason we use the same encoder is because if we used different encoders, this encoder might choose different latent features to pick out, to put here, than the Donald Trump one here. And our idea is we want to be able to take this latent face and put it into another network, or vice versa. Take this face and put it in another network. I'm going to show you that right now. So our goal, remember, is to get Nicolas Cage's face on Donald Trump's body. Okay? So what we're going to do, we're going to take Donald Trump's face, and there's work to do to get that to blend in with the rest of the body and so on, but nevertheless, we're going to take his face, we're going to feed it into our encoder. What comes out of here is a latent face. This latent face is useful for both kinds of decoders, right? Because we trained it with the same exact encoder. So we feed it now up into the Nicolas Cage decoder, and we get out Nicolas Cage in the same pose, right? Look in the same way. But with Nicolas Cage's eyes, we'll ignore hair for a moment since we just want faces. Okay. Nicolas Cage's lines on his face, whatever else there is. Does the concept make sense? How that works? Yeah.
Why do you look at
As a form of data augmentation, and just also to because a key part of our faces is orientation and kind of orientation and direction. Probably the biggest reason just would be data augmentation. If we had enough regular data, we wouldn't need to do that warping.
So for the final version, you take an unwarped version?
For the final version, you take an unwarped version. Yeah, we take an unwarped input because otherwise we'll get out this warped, which might be interesting, but not what we're after.
So just for training?
Just for training, we do that warping, just as we normally do data augmentation, just for training. Does that make sense? And again, for an autoencoder, the idea really is we have an identity function in there somewhere, and we have usually a bottleneck layer. And there are a lot of different things you can kind of do and come up with to do with these autoencoders. All right, generative adversarial networks. So these came out in, I think it was 2014. So the two parts of this are generative, that we have a network that is generating things, okay? Like generating faces from nothing, or from almost nothing. So we feed in a random vector, and it comes out with a face. We also have an adversary. And the adversary is saying, how good are you, generator? So think of the generator as the counterfeiter who is trying to create counterfeit bills. Okay? And the adversary is the Secret Service who is trying to distinguish fake bills from real bills. But imagine long ago, the counterfeiters weren't very good, right? They would take a blunt crayon, give it to a 2-year-old, and they'd scrawl on a piece of paper, and they'd say, here, this is my currency. Okay? Easy to tell the difference between that and a $100 bill, right? Well, you'd think, but the discriminators, the adversaries, weren't very good either. The Secret Service is like, I mean, I see this green $100 bill. I'm not sure whether that's real or not. I see this scribble. I'm not sure whether that's real or not. Okay? But as it gets better, the generator is going to have to get better. And as the generator gets better, the adversary is going to have to get better. So you have this arms race where they are training each other to be better and better. Okay, let's show a picture of this just a minute. What can it be used for? Generating celebrity faces. So we're basically training the generator, generate what looks like a good celebrity face. And the discriminator being able to tell real celebrity faces from fake celebrity faces. Or generating images based on captions. So here, we feed in this small bird as a pink breast and crown and black primaries and secondaries. So that is the input to our generator, and the generator then spits out potential images. Does the idea make sense? All right, so how does it work? We've got a generator neural network. The particulars of this neural network, we don't care about. If we're generating sequence data, this will probably be a RNN. If we are generating images, well, there's actually convolutions. There are deconvolutions as well. So it'll kind of be a neural network, a convolution neural network run backwards, okay? Where the output is an image and the input would be some numbers. Our input is normally called Z, and it's often just noise, just random numbers that the generator can work with. Different random numbers, you'd expect to get different output. But we don't normally assign any meaning to those numbers. And then we've got a discriminator, okay? Also our adversary. So sometimes they call it discriminators or discriminator, critic, adversary, all the same thing. And our discriminator takes a single input and says, probability, is it real, is it fake? So this is trying to show we can take input from either some training data, which is real, and then we want the discriminator to say 1, or generated output that's fake, and we want the discriminator to just say 0. True.
Does it take both at the same time?
No, just one. It's just, it can take either one. It can take a fake or it can take a real. We know during training whether it's a fake or whether it's a real, so we know the desired Y. and it comes out with a y hat, and we have a loss function to try and train it. In fact, let's look at the discriminator and train the discriminator first, because that's easier. We know how to feed in training data, right? Let's say we're generating images of celebrities. We have a bunch of, in fact, we have them from our last problem we just did. We got a bunch of Nicolas Cage. We got Donald Trump, who actually is a celebrity, I guess. We got other images. And so we'll just pick one and feed it in here and say, I want you to be learning a 1 for this, right? That's its label. And then we can run the generator and feed in its output and say, this should be a 0. And we can train it in that fashion, right? So for the discriminator, our loss function would be how good is it distinguishing fakes from reals. Fake is a real X. Okay? So the discriminator should say 1. If we have a generated Z, that is something coming out of the generator network, we want it to be 0. So binary cross entropy seems to make sense for that. So we can train the discriminator. How are we going to train the generator? Let's just think about that a second. Its job is to fool the discriminator, right? To create a $100 bill good enough to fool the discriminator, however good the discriminator is at this point in time. There's no reason for it to do any better than getting the discriminator to say 1, right? And it doesn't really even know what currency should look like. The only feedback it has is, how good were you at fooling the discriminator? And so what we can look at is take G of Z, apply the discriminator to it, and we want the discriminator to say what? 1. So if they say 1, log of 1 is 0, and so we will have a very small, like no loss. On the other hand, the discriminator says 1/4. Now let's even make it 1 over E for no particular reason. Then log of 1 over E will be -1, negative is 1, so we have a higher loss. And the key is, so we use this as our loss function. When we take dl d theta for G, we are going to be back propagating through the discriminator, aren't we? Because our loss was of D of G of Z. And so it's of this output. And then so when we do our back propagation, we're going to be going propagating through here. Now, we don't want to do any updating of the discriminator. We're training the generator right now, right? We're looking at a loss function for the generator, and so we're going to just ignore updating anything here. But then we get back to here, and we start running through here, and we've got back propagation, and it changes this for the better, right? We have moved the needle slightly such that for that input, we'd be more likely to fool the discriminator. Make sense? And we just pit these suckers against each other. And as one gets better, the other gets worse, right? In the sense if the discriminator does a better job, that means it's catching more fakes. And if the generator does a better job, it's letting more fakes pass through. So the training loop kind of looks like, and for various reasons, and there's often some annealing and everything here, but for various reasons, we normally train the discriminator more often than the generator. We'll do like k times of training the discriminator, 1 training the generator, k times of training 1. That k number may change over time, right? Part of our schedule. So we basically train D with some samples. We train D with a real image, and we train D with a fake image. How do we get Z for this? Yeah, it's just no. It's a random selection from our potential input. Right. So if we've got a vector of 300 numbers between 0 and 1, we'll just randomly choose a vector from that universe. So we randomly sample Z, create a fake image, train D, that should be a 0. Do that k times. Now the discriminator is slightly better than it used to be, right? Because it used to have, basically random. And now we train G with, again, some randomly initialized Z. Now G is a little better. And we continue on and on and on. Okay. Questions right now? Yes. Not quite hearing you, Diddy. Z, yes, thank you. So we're training G with some randomly sampled Z. Here's a flaw. This flaw doesn't work. This doesn't work well with currency. Yes, it does. So let's say we've got a world global counterfeiting enterprise. All right? So they're not just generating US $100 bills. They're creating $1 bills as well. And they're creating Canadian bills and euros. And while they're at it, they're coining stuff too. So they're also creating quarters and half dollars and loonies and toonies and all these things. Okay? So we've got kind of a universe of thousands of different counterfeitable things. We've got a training set of same of those. So we have got lots of different $100 bills and $1 bills and quarters and old quarters and new quarters and old pennies and new pennies, and maybe we even have some Roman denarius. What are these? Denarii. And the generator may find that why bother with these Roman denarii and euros? I'll just stick to US currency. I'm not even doing coins. I've got basically 1, 5, I'll do 2s. 1s, 2s, 5s, 10s, 50s, and 100s, and 20s. Okay, so it's got like 8 things that it generates, and it doesn't bother generating anything else. How good will this loss function be? Assuming it's very good at those 8. Okay, it's like picture perfect. $100 bills, $10 bills, $20 bills. It'll just do those. There's no penalty here that says all this other universe too, you should be generating that, right? Especially if it's not very good at it, right? And it gets caught often. And then it's like, well, I'd be better off just not be doing this. So it's possible to get into what's called mode collapse, where the generator outputs close to the same thing regardless of its input. So we've got all of this random information that we think should be causing it to generate all of our types of currency across all of our countries, and it actually just kind of collapses down and decides to do just, US currency or just hundreds and 500s from every place or whatever it chooses to do. Generates one different celebrity face, but it's a really good face. Now let's say it generates one really good face. All right, I'm going to show you my really good face. So, all right, that's the one really good face that it generates. And it generates slight variations on this, but this is basically it. Can the discriminator catch it? If you were the discriminator, what would you do? This is exactly what I do. I'd say, oh, I don't take $100 bills, right? That's what you go some places. The rest of the world say, sorry, we don't take those. They're counterfeited a lot. But this one is real. But sorry, it's a 90% chance it's a fake, so I'm not going to take it at all. So the discriminator could just say anything that looks like this, we're going to call it a fake. and it would do good in its loss. Because most of the time, it's seeing lots of stuff from randomly around, but whenever it sees a $100 bill, right, this is my facial equivalent of a $100 bill, then it knows it's probably bad. And what that can do, though, is cause the generator to move and say, okay, I'm not going to do $100 bills. I'm going to switch, because they're not that different, and do, right, the sad face, $50 bills. And so you can get the discriminator kind of chasing the generator around its landscape, doing different things. But the problem is, once the generator collapses to only doing one kind of thing, we're out of luck. Because there's no way to force it to be doing multiple things. So training these GANs can be difficult. And part of what you'd have to do there with mode collapse is revert back to a time when it was still generating multiple things. We'll see some examples of GANs on Wednesday. Any questions? You guys have the homework due Tuesday night? No, sorry, due Wednesday in class? Wednesday in class, not Tuesday night. You've got all Wednesday morning to work on that. All right, I'll be in my office till about 2.